Continue with diffusion. So diffusion is just the result of Langevin dynamics. So you can see that what we see here is that if you put a particle in a heat bath, like smaller particles hitting it, it will do this random walk motion, the Brownian motion. And if you look at the average of x over time, I mean, it can go to the right, it can go to the left, up, down. The average is 0. However, the average of the square of the distance is not 0. Okay? Average of the square is actually linearly increasing with time. That's why when you put milk in your coffee, it doesn't just stay as, you know, a dot, just spreads out. What I just realized while telling you that is when you have latte, there is this bubbly part and they do something, the pattern on it just stays, right? Why does it stay? Because the bubbly part doesn't have the same dynamics as the fluid part. The fluid part has these particles hitting and spreading everything out, but the bubbly part doesn't have that. Okay? It's an interesting observation. So, in short, we know that the expectation value of x over time is 0, but the expectation value of x squared over time, as time goes to infinity, it approaches 2 times diffusion constant times t. This is the diffusion constant that you all know, that appears in diffusion equation. So we will now find the relationship with diffusion constant and this microscopic friction. We first need to find del squared, the expectation value of x. Okay, x squared. What is the expectation value of x squared? Let's find it. What is our equation? Our equation is mv dot equals to minus gamma v plus RT. Do you remember this? Let me write it down as m x double dot equals minus gamma x dot plus R of t. Do you have any objection to this? No. Now we are going to use a trick. Okay? The trick is to multiply both sides by x. If you do that, then it's mx x double dot equals minus gamma x x dot plus x of t R of t. Then I'm going to write this x x double dot as yet another trick. This is yet another trick. d over dt x x dot minus x dot squared, yes, v squared. So can I write that?
Yes.
Yes, because let me write in green here. I can write that because dx x dot is over dt is x dot times x dot plus x x double dot. Do you see now? So I have replaced this part by this one minus that one. Okay? We are going somewhere with it. Equals to minus gamma x, the right hand side remains the same. Okay, what I'll do now is I'm going to take this to the other side. and take this one to the left. M d over dt x dot plus gamma x dot equals to m x dot squared plus r of t x of t. Okay. Now let me get the expectation value of this. Okay. The expectation value of, so I'm finding the expectation value of this system. M x dot squared we are almost there. So what is this? You don't need to know this. I mean, you don't need to guess my mind, but is it kBt? Do you remember the expectation value of mv squared over 2, the kinetic energy for each particle, was kBt over 2, equipartition. So mv squared expectation value is, kBt. And how about this one? R average is 0, X average is 0. Remember? R times X, R is uncorrelated. No matter what you write next to it, it's 0. Okay? Tell me.
How are we certain of this?
Okay. Why we shouldn't be? Okay, let me tell you. X is a variable that has an average of 0, right?
Yeah.
R is a random variable that has an average of 0.
That doesn't mean their product also has average of 0.
That does mean because R is uncorrelated to X.
How do we know R is uncorrelated to X?
R is uncorrelated with anything. R is completely random.
All right.
Okay? Very good. So let me call this y, and let me write that equation down again. M times dy, M times dy over dt plus gamma y equals kBt. Okay? Let me rewrite it like this. dy over y minus kBt over m is equal to minus dt gamma over m. Do you see how I did that?
Yes.
Yes. So y is, if you integrate it, y is kBt over gamma times 1 minus e to the minus gamma t over m. Almost there. Now what was y? Y was x dot. Can I say that x dot expectation is 1/2 d over dt of x squared expectation?
Yes.
Yes? So then d over dt of x squared expectation is 2 kBt over gamma times 1 minus e to the minus gamma t over m. Lo and behold, we are there. X squared is 2 kBt over gamma times t plus 2 kBt m over gamma squared e to the minus gamma t over m minus 1. Okay? I just integrated the right-hand side.
I have a question.
Sure.
Do we know the initial values for,
Yes.
what are the initial values for them?
The initial value for x squared is 0 because we start from the center. We define it as starting from the center. Very good. Very good. Now,
these averages, they are taken over an ensemble, right?
yes. Yes. Very good. Very good. So, then let's look at the t goes to 0 case. Okay? So, we just barely started. It hasn't diffused yet. Just at the beginning, it might have some velocity. So we actually expect x to be proportional to t squared at the beginning, the very beginning, because at the very beginning it's ballistic. It's not like tuk 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 tuk. It's started just doing that, so it should be t squared. You are super bored, so anyways, let me do it. So for t very, very small, what you get is this. T plus m over gamma times 1 minus gamma t over m plus gamma squared t squared over m squared plus minus 1. I mean plus dot 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 minus 1. Okay. So can you please tell me what is this? Taylor expansion of the exponential. Okay. So what happens is that this one cancels that one. Okay. This one cancels that one. And you do get at the beginning x squared expectation value as t goes to 0 is indeed kbt over m times gamma times t squared. But that's not really super interesting to us. We are more interested in t goes to infinity case, which is easier to show. T goes to infinity case. So if you wait for long enough, then x squared expectation value is so this term is going to go to 0 as t goes to infinity, right? And this t will be much larger than whatever remains. So it's just simply 2 kbt over gamma times t. Okay? Remember, we said that we are looking for this kind of an equation. Okay? So diffusion, then let me just summarize everything. Oh, thank you very much. Yeah. Yeah, no, you are right, you are right. 2 factorial is there and 2 goes with 2. Yes, very good. So far so good? Yeah. So this whole chapter hopefully taught you about dissipation or drag, right? Which is basically the minus gamma v term, okay? Then there is fluctuation, which is this square root 2 kbt gamma, let me say, over delta t times a Gaussian. Okay? And finally diffusion, which is d equals to kbt over gamma. My point here is that this microscopic friction gamma appears in each one of them. And it's basically telling you that those microscopic interaction, those kicks, are responsible for all these things, and they are all related to each other. Okay? You might be asking, you might ask me, can we derive gamma from our system? Does gamma itself has an equation? We just wrote gamma, right? What is gamma? For example, gamma, if you are dealing with, it's called Stokes theorem. Stokes relation, right? This is Stokes formula. So you can derive gamma from Navier-Stokes equation. You can just put a ball inside the fluid and see what happens to it when you drag it. And you will see that gamma is actually related to 6 times pi times mu times a. And a is the radius of the ball. Mu is viscosity of the fluid. Okay? But we have an ideal gas. So for ideal gas, you have another equation for gamma. And let's not go into that. Okay? So I'm skipping a couple of pages here. Yes?
But in that case, we need to know the viscosity of the fluid. So
Yeah. So what is viscosity? And is that your question? So you can derive viscosity from microscopic interactions, okay? Or in the case of ideal gas, it's actually related to, according to ChatGPT, mean free path, and you can derive mean free path from statistical mechanics. So you can derive, for ideal gas, you can derive gamma using statistical mechanics.
ideal gas has no viscosity.
Ideal gas has no viscosity, maybe, but ideal gas have this gamma. Okay?
So this works only for viscosity is greater than zero.
I'm sure there are a bunch of things, like for example, this is probably for incompressible fluid, okay? Ideal gas is not an incompressible fluid, okay? So it's they are super related, Navier-Stokes equation and ideal gas stuff, I'm sure. There's a bridge there, but they are also worlds apart. There's a bridge, but they are far away. Okay. Shall we do, if you don't have any questions, we can move to the new chapter.
Also, can you open this patient part again? I'm looking for this patient.
This one?
Yeah. All right. I just want to make sure.
Yeah. You are happy though, right? This is the first time you are not answering to that question.
Interestingly enough, when we take gamma to be 0, then we get 0 drag force, which is consistent with the Lambert's paradox. But then it means there's no fluctuation in ideal gas and infinite diffusion, so it blows up.
Yeah. Yeah, there is infinite diffusion if gamma goes to 0 because there is no drag, so nothing is dragging your system. So if you, your x is actually going to be proportional to t squared. It's ballistic transport. So a better way of thinking about it is naming stuff and taking each one of them separately. Like, I'm in the ballistic regime, I'm in the diffusion regime. This is a Levy flight or whatever. Okay, all those are different subjects. Good? Any other questions? Who wants to go home and sleep? Please go home and sleep.
Does this explain the T2 decay?
Huh?
T2 decay in MRI signal, the signal decays because of the MRI signal, T2 time constant, so different parts.
Okay, okay. So help me out here. So in the MRI, you are starting this rotation and it just stops at some point, and there is some relaxation time. Yes, in some way these things are related in one way or another. Like, yes, this is just giving you the general mechanism of dissipation. Okay.
Does blood have higher T2 than gray matter?
Ah, okay, you mean that way. Yes, that way for sure. But we are talking about this precession of the nuclear spin, right? So it's complicated. It's complicated because there is this giant vacuum, then there's electron cloud, and then in the middle there is this spin. I mean, it's complicated stuff. You know, that spin is not directly interacting. They are not touching or anything, right? There's some complicated exchange correlation thing between the spins, the nuclear spin, the angular momentum of electrons, right? Okay, I've just walked around your question. Sorry about that. But the mechanism is that it goes back to second law of thermodynamics at the end of the day. Can gas atoms come together and push a ball with very high velocity? Yes, they can. Would they? No, they would not. Okay? I mean, it's a possibility that everything somehow arranged so that at that particular moment gas atoms collide with the ball and provide a force with a memory. So sudden, out of nowhere, this one starts spookily going like that, right? So I have something on the table and it starts magically moving away. Okay, that would be magical, right? However, it's not at all magical when we move it and it stops. Although it's the same thing, right? It was moving. According to Newton's law, it should keep moving, but something is magically stopping it. Are you with me or not? You are. I mean, what is stopping it can move it. Okay? If you turn back time, it should move back. Because what is the table doing? It's sucking up the mechanical energy and it's spreading it out. Right? It's just as well could come together and make this move backwards. I mean, there's no physical law against it. It's just there's a mathematical law against it. It's mathematically impossible, not physically impossible. Are you with me or yes?
So brakes of a car should accelerate a car?
Say it again.
Brakes of a car should accelerate the car?
Could accelerate the car physically. Well, brakes is a different story because you are pressing them. But yeah, like let's say you put something on top of the car. So let's say let's say you put a brick on the brake, so the brakes are there. The car is moving forward. You take this thing, I will talk about that kind of friction now. There are these protrusions and things like that. Now, what happened every time you have created non-equilibrium movement, it spread out and created heat. Now let's get that time backwards. Okay, so this is now going, just like you pushed it and it started jiggling and it spread out. Now it will start jiggling and push it back. Okay, physically not impossible. Newton's laws are Newton's law have time symmetry. If you put t to minus t, it's exactly the same.
Is the question why drag force always in the opposite direction?
Mm-hmm.
Oh. I think we can also say that if we have a random ball that's moving at velocity v, then we can go to its reference frame.
Yes.
After that, the particles will have an average velocity of minus v in that case. And of course, theoretically, if we are really, really lucky, then, for example, the particles that are not going to hit it will have velocity minus v at there, and only ones that can hit it. But it's statistically impossible.
It's statistically, mathematically impossible. Yeah. Physically not. Okay, yeah. Right? My code is not perfect, so I can't really show you this. Before, my code was perfect, and I could show students, like, I would start with initial velocity, and the ball would go, okay, and then I would stop the code, and I would say, now I will turn time backwards, and the ball that was stopping would move like this, okay? Would you like to see it? No. Come on. No, the answer is no. The answer is always no. Okay. Brownian motion, we have dt over 2, and this is time reversal. Do you see? Everything reverses velocities. So let's have some initial velocity. Let's say 1. Oops, no. Let me put another thing to stop time. If it's w, then dt is 0. Okay? .1 and more particles, please. Okay. Okay, didn't move, so let's do it again. But more particles means it will have less effect. More drag and, okay. Where is my velocity? Yeah, here it is. Let's do it again with 1.0. Okay, so now I reverse time. It's stopped, right? Now I reverse time. It didn't work. The thing is that there are just too many things going on here. Let me interrupt, and let's put few particles again. Number of balls are less, and velocity is small, 0.1. Just watch the particles when I move back. Do you see that there are unreasonable amount of particles moving it backwards?
Yes.
You see? Okay.
There's nothing banning this.
Hmm?
Physically, that's not impossible.
Yes, physically it's not impossible. It's just the thing is that once I move this ball like this, I create a very special non-equilibrium condition.
Which has really low entropy.
Really low entropy, really low probability of happening. And when I reverse it, it seems like gas atoms somehow decided to push it in this direction. I haven't demonstrated. I mean, it was a very bad demonstration. So I will have another try, one final try. Was 0.1. If I can't demonstrate with this, I can't really demonstrate it. I stop time. Reverse, no, okay. Okay. If you understood it, it's fine. Should we go to the next chapter? No, you don't want the next chapter. Not today? Then I will talk about this one more. What is special about today? Did I do something wrong? So did it stop? Reverse. You see, if the code was perfect, it should just trace it back. It doesn't, so it's hopeless.
Can we reduce the dt?
Oh, yes, we can. Will it work? So should I start it going back?
Let's try.
Let's try. Do you notice anything on the right hand side, like more particles hitting from the right? No?
This thing is chaotic.
This thing is what?
Chaotic.
Chaotic, yes. 0.1, and let me just... Okay, I will not show you the stopping of the ball, but I will show you something else. It's going to the right, and it's going to hit a bunch of particles on its way. Do you see? Lots of particles are being hit at the right. Now I will reverse the time. Okay? Now I reverse the time. For some reason, there will be more particles hitting it from the right. Do you see? Or not? You don't see?
I do.
Bir de içeride toplar oluyor ya, onlar dışarı çıkıyorlar. Biz geri sardığımızda bu sefer geri içeri giremedikleri için onlar da yön değişmesi.
Okay. Now it's going to the left. Let's just wait for it to go to the left. This time we don't have that problem, right? Lots of particles hitting on the left. So now I reverse time. You see, normally the ball would have lots of particles on its path, but it's empty because it just cleared them out. You see, as the ball moves in one direction, it clears out its background, which is not what is expected from entropy maximization, right? There should be particles everywhere, but that part is empty. Yes or no? Are you convinced?
Yes.
Now you want to go home and sleep? The next chapter was very nice, but we will have time for it.
We can spare hour if you want.
For no. We, by the way, we are ahead of time.
Oh, all right, all right.
Okay.